But I realized this morning that I have been actually updating my Canvas course website after every lecture. But then I realized that it's not published to students, and so you might not have access to my update, and I'm very embarrassed about it. This shows my level of competence in IT. And so you can ask, well, if you cannot deal with Canvas, how can you solve string theory? And that would be a valid question. But anyway, so since I'm not totally sure about my confidence, I think that Canvas is a good system when you have like homeworks and assignment. But for the purpose of this course, I think a simpler setup might be more helpful. So I moved the course website to my own website. So I sent you the link, so I hope you received it. If not, please let me know. And I will update that site rather than the Canvas site so that there will not be further confusion. I hope that's okay. And some of you also asked about the course reading materials. So last quarter, I mostly used my lecture notes from Tasi summer school. And this quarter, I'm taking material from various sources. But one of the useful material that you might consider reading is part 1 and part 2 of the book entitled Mirror Symmetry, published from Clay Math Institute, 2003. I put the link to my course webpage, so you can look at it. I think that covers very well the kind of material that I have been discussing this month. Next month, when I get to D-Brain, I will give you more appropriate material, reading material for that too. Okay, so for the last couple of lectures, we have been discussing geometry of Calabi-Yau manifold from classical mathematical point of view. From physics perspective, that would be the geometry as seen by point particle. But this is a course about string theory, so we need to see how Calabi-Yau manifold are seen from the perspective of string theory. And that would be the following perspective. So Calabi-Yau as seen by string theory. So you have this complicated Calabi-Yau manifold with lots of geometric structure. And well, if you have a point particle, you map that to a point in Calabi-Yau manifold, and then you study the geometry of this. If you have a string, you consider string propagating on Calabi-Yau manifold, and then when the string propagates in space-time, it sweeps out 2 dimensions. So in the last lecture, last course, we studied how this propagation is studied from the point of view of 2D quantum field theory with conformal invariance. So this is called the CFT. And sometimes CFT2 to denote the fact that we are dealing with 2 dimensions. So from this, in this description, for example, the geometric information about Calabi-Yau is encoded in the Lagrangian of this 2-dimensional quantum field theory, and calculations such as the metric of Calabi-Yau or intersection number and various geometric quantity have analog of that in the conformal field theory perspective as physical observables of this quantum field theory. But quantity calculated from the conformal field theory perspective can be different from the corresponding quantity in the classical geometry, and we may consider this as a sort of quantum deformation to these classical observables. So this is what I mean by Calabi-Yau as seen from the perspective of string theory. So in general, of string theory, for each background, by this I mean the configuration of the metric and symmetric tensor field and the various other fields taking value in space-time correspond to a choice of CFT on the worldsheet. So this gives rise to this perspective that rather than directly studying how string propagate in space-time, we can try to study the space of all possible two-dimensional conformal field theory and discuss one appropriate to describe superstring, and then study that class, and that would correspond to the choice of background. So this leads us to consider the space of quantum field theory and quantum field theories and the space of conformal field theories. Now, space of quantum field theories and conformal field theory can be actually richer, and there may be more conformal field theory in 2 dimensions rather than higher dimensions. But it's also nice because two-dimensional conformal field theory, we have more tools because Virasoro algebra is bigger than the conformal symmetry in higher dimension. In two-dimensional conformal field theory, you have larger symmetry, but there are more conformal field theory too. And let me explain what I mean by there are more conformal field theory. So in order for quantum field theory to make sense, we need quantum field theory to be renormalizable. So what does it mean to be renormalizable? What it means is that, well, so let's consider the case when we know what the Lagrangian of quantum field theory is. So in general, it may have a scalar field. You may have mass term for the scalar field. You may have the Maxwell field, and you may have interaction between Maxwell field and the scalar field. For example, scalar field might be charged, or you might have fermions, and the fermion may couple to gauge field, so it might have covariant derivatives, and you may also have a mass for the fermion. And you may also have some kind of interaction such as the Higgs type interactions, for example. And you can have all sorts of interactions. But some interactions are good and some interactions are not so good, more difficult to deal with. And so basically those can be determined by the engineering dimension or mass dimension or energy dimension of these interaction terms. So you decide, what you do is you decide, attach the dimension to each dynamical field, and then ask what the dimension of interaction terms are. And from that, you infer the dimension of the coupling constant. And if the mass dimension of the coupling constant is non-negative, then we call those interactions as renormalizable. And those are the class of interactions for which the standard technique of renormalization works. By that I mean that when you do this, start with this Lagrangian and assume interaction terms are small, do the perturbation theory, it gives rise to ultraviolet divergence in general. You need to renormalize it. I assume you have seen this in the introductory course of quantum field theory. There is a well-defined procedure of how to deal with these ultraviolet divergences. And this system works well, and you can actually renormalize all the divergences into finite number of parameters if and only if all the coupling constant has non-negative mass dimension. Let me be more specific. So for example, let's consider d-dimensional space time, d-dimensional space time, then the action is given by this. So you can, well, we can ask what is the mass dimension of the action. One way to tell is that the action has to be dimensionless, because even if we introduce the non-natural unit where we explicitly write down h bars and things, the weight of physical amplitude is exponential of minus the action divided by Planck constant. And so in the natural unit, so therefore the S must be dimensionless. So that means that the mass dimension of Lagrangian density should be mass raised to the power of space-time dimensions. Okay? So then suppose the Lagrangian contains things like kinetic term for scalar field. Well, so this must have a mass dimension to d. So from that we infer that the mass dimension of the scalar field is m of half of d minus 1. Because each derivative gives you mass dimension 1 because it's inverse of the length. In quantum mechanics, the length times energy, length times momentum is h bar, which is dimensionless. And the momentum and the energy has the same dimension if the speed of light is 1. And so that means that the scalar field should have this dimension. Similarly, we can see that fermion should have mass dimension of d minus 1 over 2. Because you have two of them, but then you have only one derivative. So Maxwell's field, well, it's actually, there are various conventions, but one convention is that if you define covariant derivative as like that, without any terms with mass, then the mass dimension of the Maxwell field has to be equal to the same as the derivative, so this is equal to 1. Okay? So you can set up this. So then you can count, for example, what is the mass dimension of this coupling, this coupling. Okay? So for example, from this we can count that phi, psi bar, this Yukawa coupling. What is the dimension of the Yukawa coupling? Well, this should be equal to m of half of 3/2 of d. And you have 1 phi and 2 of psi, so minus 2. Right? So therefore, the mass dimension of Yukawa coupling is this. Okay? So that means that when d is equal to 2, then this is 1. D equals 3. So it's going to continue to increase, right? And okay, good. And then okay, so then we should count what is the dimension of G. Well, so S has to be dimensionless, and if you look at this, you have G times dx to the d of phi of psi bar. Okay, so this has m of half of d, 3d minus 2, and this is equal to m of minus d. So therefore, in total, this has m of 1/2 of d minus 4. Okay, so that means that the mass dimension of G is equal to m of 1/2 of 4 minus d. Okay, so what does it tell you? What it tells you is that for d greater than, for d, excuse me, less than or equal to 4, it is renormalizable. What it means is that when you have fermions and scalar field, you can turn on this interaction, and then you can do perturbation theory, and so you can deal with ultraviolet divergence of the perturbation theory when the dimension is less than or equal to 4. But when d is greater than 4, this is non-renormalizable. Okay? So that means that as far as you want to use perturbation theory and then calculate physical quantity by renormalizing divergences into finite number of parameters, it won't work in dimension greater than 4. It does not mean that theory does not necessarily make sense. There is a situation where seemingly non-renormalizable theory makes sense in some non-perturbative mechanism. And there are cases where we know that, not in this case, but in some other cases. But at least we see that there is a difficulty in the standard perturbative framework. Okay? So as you can see that in general, therefore, interactions become harder to get in higher dimension. The reason for that is that in order to have interactions, you have to have many fields. Right? Interaction means that 3 or more particles come together and do something. Right? And so if Lagrangian has only 2 terms, these are kinetic terms, or mass terms. That sets a mass dimension of these fields. And then with these mass dimensions, the interactions are determined. But the point is that except for gauge field, the scalar field and the fermion, the dimension of scalar field and the fermion increases with dimension. So since dimension of the phi and psi increases with dimension, it becomes harder and harder to have interaction between them because they typically generate non-renormalizable interactions. So that's a problem. Okay, and the situation where the coupling constant, if mass dimension is equal to 0, then the interaction is potentially conformal. It means that if the coupling constant is if the coupling constant has conformal means that it is invariant under scale transformation. If the coupling constant has a dimension of mass, if you change the scale of the theory, then the coupling constant has to scale. So it doesn't stay constant under renormalization, therefore. So therefore, such coupling constant would not generate conformally invariant perturbation interactions. If the coupling constant has 0 conformal engineering dimensions, then there is a potential that such interactions are conformal. I said potential because it turns out that in order to actually genuinely such interaction to genuinely generate conformal interaction, you need to satisfy other conditions. But so this is an interesting situation. So that means that suppose you have action or Lagrangian of conformal field theory. So suppose you start with conformal field theory. Suppose you start with CFT. With some Lagrangian, with some action, which is given by this integral of Lagrangian density. And then suppose you perturb it. By that I mean add some interaction with coupling constant. Okay, and if the conformal dimension of this interaction is d, then integral of O over d-dimensional space-time is 0. Then the dimension of the integral of O in space-time is 0. So that means that the coupling constant has 0 conformal dimension. So there is a potential that this generates the conformal invariant perturbation. So this can generate conformal invariant perturbation. This might generate conformal invariant perturbation. But we need more conditions. So how do you figure out the condition? Well, so this is an interesting situation, because if that happens, what happens is that if this generates genuinely conformal invariant perturbation, then it means that actually the conformal field theory is not just one theory isolated and sitting over there, but you can actually have a family of conformal field theory parameterized by this parameter lambda. So you get some kind of family, one continuous family of conformal. So what kind of condition do you need to satisfy? Well, this is what Ken Wilson taught us, which is to study the renormalization group. Okay? So, what is the renormalization group? So renormalization group is the following concept that I'm assuming that you have taken introductory course of quantum field theory, so you must have learned the renormalization. And in order to do renormalization, what you do is that first you introduce some ultraviolet cutoff. So let me write down the procedure of renormalization. So first step is the cutoff momentum space by something like the momentum P is supposed to be less than some ultraviolet cutoff. And you just allow loop momentum to be integrated only in this cutoff regime. Of course, eventually you would like to take this to be sufficiently large, so much larger than any energy scale that you observe. So if you do that, typically in loop amplitude, there are terms that appears to be lambda dependent in such a way that if you take lambda to be infinite, all these terms becomes infinite and does not make sense. And in order to avoid that, what you do is to renormalize a mass, coupling constant, and wave function, etc. By in lambda dependent way, so that lambda UV going to infinity makes sense. So this is a renormalization procedure. Okay, so basically you just define allow lambda dependence on the mass, coupling constant, and the wave function renormalization, wave function normalization, so that those things can absorb the lambda dependence. Okay, but in order to do that, you need to specify the value of these quantity at some energy scale called renormalization scale. So to do that requires setting renormalization group scale, which is called mu. Okay. So that means that after this procedure, mass and coupling constant, the wave function, etc., acquires dependence on the renormalization scale. Okay, so that means that for example, the coupling constant G now become function of renormalization scale. Okay, and so the beta function, which characterizes how the scale dependence after renormalization works is a logarithmic derivative of this coupling constant with respect to this scale. Okay? So the conformal invariance require that this is equal to 0. Because the renormalization scale is by definition has dimension of energy and mass. So if the theory is conformal invariant, the coupling constant, renormalized coupling constant should not have such dependence. So this is a necessary condition for the coupling constant, conformal invariance. And so you can calculate this. You can calculate this in perturbative expansion. So the leading term is proportional to delta minus d times g. And then, but this does not end here, and there are some higher order terms, so something like order g squared, etc. And so what is this? So delta is the conformal dimension of the interaction when you deform CFT by CFT plus G of O. Okay? So this shows that when conformal dimension or mass dimension of this interaction is D, which is this case, then to the leading order in the perturbative expansion, it is indeed conformal. Okay? But there can be some higher order terms that you need to calculate that might spoil the conformal invariance. And in general, in order to check the conformal invariance, you need to study this to all order and see what kind of terms that appear. Okay, but potentially this is a first step. Finding interaction where delta is equal to g is a first step. Okay, so I have been telling you this because I wanted to tell you that two-dimensional situation is in some sense richer, and it is richer because there are more ways to find the operator whose conformal dimension is D. And the reason is that in 2D, so remember that the conformal dimension of a scalar field is 1/2 of D minus 1. So this means that at D equal 2, the conformal dimension of a scalar field is actually 0. So that means that you can actually have as many files as you like, and all these operators have no conformal dimensions. That does not change the conformal dimension. So I'll give you an example. So suppose you start with a Lagrangian. And suppose you have a kinetic term for this Lagrangian. Okay, so in 2 dimension, the action is 2-dimensional integral of L. You want this to be dimensionless. So that means that this has to have dimension 2. But you already have two derivatives. So we can see already that phi has no dimension. So this shows that there are actually many things you can do. So for example, you can actually change this to L, which depends on phi. So for example, you can actually, so this means that, for example, you can actually change L by adding any function of f. And potentially, this is conformal. potentially conformal. Okay? And you can be more ambitious and do the following. So suppose you have a D scalar field. Then you can even consider Lagrangian, which takes the following form. Oh. So here I should use a different notation. So suppose you have phi scalar field for phi A with A go from 1 to D. Then you can consider Lagrangian of this form. So any D by D matrix which depends on phi can be multiplied to this, and this is a candidate for conformal invariant Lagrangian. Because at least when you write down this Lagrangian, you don't have to use any parameters which has dimension of mass. So G can be many complicated function, comes with many parameters, but since these are like expanded, we can expand it in power series in phi, for example. The coefficients are all dimensionless because phi is dimensionless. And so therefore these are again potentially conformal. Okay? But this is very interesting situation because it is as if there are infinitely many coupling constants. Because you can consider this, say, for example, in expanding in power phi. So what if you expand in power phi, the leading order is a constant matrix, but you can have A, B, C, phi C, and you can have A, B, C, D, phi C, phi D, etc., for example. And these are all arbitrary constant matrices, at least when you just write down the Lagrangian. And these are all dimensionless coupling constants. So you can have infinitely many coupling constants. So, but there is nothing prevent you from doing perturbative calculation, for example, with this Lagrangian, and do the renormalization. You can do that, and the renormalization procedure works perfectly because all the interaction has zero mass dimension, so these are renormalizable. It's just that you need to renormalize ultraviolet divergences into all these infinite parameters. Okay, but there is nothing wrong with this, and we can do the perturbation, and we can calculate the beta function. So this is actually a very simple calculation you can do, and so how do you do the renormalization calculation? So for example, one loop beta function. Okay, so how many of you have either taken introductory course of quantum field theory or read an introductory textbook on quantum field theory, such as Pesky Schrader have read? You have studied the renormalization of QED. You probably studied this. And so in QED, so what's the one loop diagram? Well, one loop diagram may have something like, for example, this. So this renormalizes mass. You can also have a photon propagator like that, etc. Right? So you can have those kind of things. So you do the same thing here. So for example, if you have this interaction, then what you have is that you can have a scalar field coming in. So you have a phi coming in, and then you have a one loop amplitude. Well, I guess it's a scalar, so you don't have an arrow. And you have phi, and you can have phi going around here, and you can have 3-point interaction given by, for example, something like that. Okay, so you can calculate this, and from that you can reduce the renormalization of GAB del mu by A del mu by B. Okay? And so then what happens is that now GAB phi becomes function of renormalization scale, and you can calculate the beta function. So beta function now has index as well as it's actually a function of phi. So you obtain function of phi. So can you guess what this beta function is? What would be the most natural thing you can think of? This quantity. There is a GR specialist there, so he must have guessed what this is. So namely that this is actually rich tensor. Well, there is a normalization coefficient, but there is a rich tensor. You can calculate this, and then what I mean is that you pretend this as a metric in some space of phi. So you have finite, so you think GAB as a metric in a d-dimensional space, in a d-dimensional space of phi. D is a number of phi's, right? This has all the desired property of the metric because it's symmetric, because it's contracted by symmetric thing. It has to be positive definite, namely that it's symmetric so you can diagonalize it. It requires eigenvalues are all positive real numbers because it's a kinetic term for scalar field, so the kinetic term has to be positive in order for the unitarity to work. So unitarity of quantum mechanics requires that GAB to be symmetric positive matrix, so this is, we are entitled to call as metric in the space of scalar. And space of scalar field is d-dimensional. So you have some kind of d-dimensional space from the metric, so you can use the standard GR or Riemann geometry to calculate Riemann tensor. Okay, so this is actually a one loop. So if you do one loop beta function calculation like this, then you find that the beta function is actually rich tensor. So that means that conformal invariance of this theory at one loop requires that this d-dimensional space, which we call M, did I use M for something else? I used M for the mass. So maybe curly M, requires that M is an Einstein manifold. Right? Because rich tensor must vanish. So conformal invariance requires that RAB is equal to 0. So this is actually a vacuum Einstein equation. So conformal invariance requires that vacuum Einstein equation is satisfied. Okay, so this is nice. So, well, is this something that appealed to you? I don't know. It appealed to me. This was very interesting insight. And this actually seems to make sense because remember why we are doing this? The reason we are doing this is that we are considering string propagating in space-time. And if the string is propagating in some space-time with some metric, then what do you have? Well, first of all, you have the coordinate describes the position of the string worldsheet. And that coordinate turns into scalar field. If the target space in which string is propagating is d-dimensional, Then you have D massless scalar field. If the target space is flat Minkowski space, and this is what we considered the last lecture, last class, the last course in the winter quarter, then the Lagrangian is a free field theory of this scalar field with kinetic term to be just diagonal. And in fact, the kinetic term is given by Minkowski metric of the spacetime. So what I'm doing here is just consider more general Riemannian manifold. So this would describe actually a string worldsheet in more general Riemannian manifold, not just flat space, but more general Riemannian manifold. You can ask, well, how you describe, so this is an answer to the question of how to describe string in a more general background. So if you have the curved space described by some Riemannian metric, then this is a natural Lagrangian to consider. Now, in string theory, the low energy approximation of string theory is Einstein gravity coupled to finite number matter field. So there must be a place where Einstein equation plays a role. And we just found one. We just found that in order for this string propagation in space-time makes sense, we need to have conformal invariance on the worldsheet. And we just found, and this is something you actually can relatively easily calculate, that if you calculate the beta function at one loop of this theory, you actually find Riemann curvature, rich curvature, on the nodes. And therefore, conformal invariance requires the Einstein equation, vacuum Einstein equation. We are not turning on other background. We are not turning on scalar field or Maxwell field. So it's natural that you are just getting vacuum Einstein equation because there are no other excitations around. It's natural to expect that if you turn on other matter field as a background, the equation is modified to include energy momentum tensor for other field. And indeed, it is the case. You can actually find more general background. And again, interpret that as a worldsheet interactions and calculate the beta function. You reproduce more general non-vacuum Einstein equation with this replaced by RAB minus 1/2 of G mu nu R is equal to the stress energy tensor for that background. Okay, so everything seems to work out. So let me actually see that a little bit more explicitly here. So this was, it may have come out a little bit mysterious because I didn't do one loop calculation, I just declared that it is rich tensor. But there is some simple calculation you can actually do to check this thing. So I told you that if you have this kind of perturbation, to the leading order, the first term you get is the requirement that the interaction term is conformal. So you can ask what kind of condition that you'd have. Okay, so let's actually consider the following situation, the simpler situation. So this was a rather sort of a general statement, but it's always useful to actually study some simple case in detail. So let's again consider Minkowski space. So string in Minkowski space. Okay, so in that case, if you have bosonic string, the Lagrangian is just 1/2 of del mu xa, del mu xa, where, or maybe I should write for later purpose, eta ab del mu xa, del mu xb, where mu goes to 0 to 1, the worldsheet coordinate, and eta is Minkowski metric, and I'm always using almost positive convention. Okay, so now so this is conformal. This we know. We studied this in the last quarter, and we might consider deforming it. So what kind of deformation we can have? Well, we can consider adding some interactions, like for example, a dilaton or a scalar field with momentum k, and integrate over two-dimensional space-time phi k e to the I kx. Or you can also consider adding some interaction like that, but quadratic in derivatives. So this can depend on the momentum. So you can consider these as interactions, for example. Okay, so for simplicity, let's say that A is equal to here 0, 1, d minus 1. Okay, so A goes from 0 to d minus 1. 0 is the time direction. Okay, okay, so let's count the mass dimension of these fellows. Okay, so the mass dimension of this object, this quantity, is something we discussed, I guess, in the last quarter. So this is actually equal to k squared. Or in the Minkowski metric, so this is equal to minus k0 squared plus k1 squared. So I write k vector squared. So let me write this as eta ab k a k b, which is equal to minus k0 squared plus k vector squared. Okay. So that means that in order for the conformal, in order for this perturbation to be conformal, you require this to be minus k0 square plus k vec square minus 2, because I erased this one, excuse me. Oh, yeah, you want this to be you want this to be 0, but if this is conformal dimension then in fact you should have the condition is that this conformal dimension of this mass dimension of this is 2 minus conformal dimension. So you have 2 minus conformal dimension. Okay. So let's see if I'm doing this correctly. Yes. Let's see. Yeah. So this means that k0 square is equal to k square minus 2. So this indeed shows that it's tachyon. Because this momentum square is less than 2, this is negative. So that means that energy becomes pure imaginary for small enough momentum, and so it's unstable. So this is actually a tachyon. And indeed, we saw that the bosonic string contains tachyon, and we actually find tachyon over here. So you can think of this as a tachyon buffer. How about the HAD? Well, so let's calculate the conformal dimension of del mu xa, del mu xb e to the I kx. Okay. Okay, so that's easy to calculate because each of them give rise to 1, so you have 2. And then that one, so you have 2 minus k0 squared plus kx squared. Okay, and then this is multiplied by HAB. So you have this type of interaction. So therefore, the conformal dimension of HAB is 2 minus this, which is equal to k0 squared minus kx squared. And that has to be equal to 0. So that means that HAB is massless. But it has 2 more conditions. One condition comes from the fact that it has to be actually primary field of conformal field theory, which means that it must be annihilated by bilateral algebra. And also another condition is that it cannot be trivial. By that I mean the following. Suppose I have operator like that. And suppose I take a derivative of this operator with respect to mu. Then it gives rise to something like ik mu e to the ikx, right? And ik mu, excuse me, ik mu, ika del mu xa e to the ikx. Yeah, let me do it. Okay. So if I have operator like that, if I take derivative on the worldsheet coordinate mu, then I get something like ika del mu xa e to the ikx. Okay, so that therefore if you have something like that, you can write it as a derivative. So that means that if you change HAB by HAB plus Ka epsilon b plus epsilon a kb, then these are actually trivial deformation. These are trivial deformations because these will be just adding total derivative for the interaction term, but action is given by integral of Lagrangian density. So the total derivative, adding total derivative would not modify the action as far as the worldsheet doesn't have boundaries. So this is actually trivial deformation. Yes?
Sorry, is this some kind of gauge symmetry?
Yes, indeed. So that was what I was coming to. So from the worldsheet perspective, this just means that this is a trivial deformation of the perturbation. But if you think of GAB as graviton field in space-time, because that's where I'm trying to come to, because you want to think of HAB as deformation of Minkowski metric. You're adding this to Minkowski metric. So that means that you are deforming eta AB to eta AB plus HAB. So this is sort of, so for example, that GR person studied the gravitational wave coming from binary black hole. So he must know how to think of this as sort of gravitational waves propagating around the Minkowski space. And quantizing that gravitational wave gives rise to gravitons. So graviton has this gauge invariance. And so this gauge invariance from the point of view of string worldsheet is just a statement that this type of deformation is not a genuine deformation of quantum field theory, because you're just adding total derivative to your Lagrangian density. Another constraint you have to have is that in general, if you deform CFT Lagrangian by adding CFT plus some coupling constant times O has to be a primary field of stress energy tensor, which means that it has to have a nice operator product expansion. That it has to have operator product expansion, which looks like this. So this in particular means that if you calculate the contour integral, Cauchy integral of energy momentum tensor around this point with a multiplication of z minus w square, then it should vanish because there is no third order pole here. And if you work out this condition, you find that this condition in this particular case is a condition that HKA, HAB is equal to 0. So this is actually Lorentz gauge condition. So what's the summary? So summary of what we saw was that if you have a Minkowski space Lagrangian, which is equal to eta AB del mu XA del mu XB, and if you deform this Lagrangian by adding Minkowski with d square x HAB k del mu XA del mu XB e to the IKX, then this will be the same. Then what you find is that condition that this operator is O, this operator O has conformal dimension 2, is equivalent to say that k square is equal to 0, namely that it is massless. And the condition that O is not total derivative of some other field implies that that KHAB, or rather I should say that this Lagrangian is invariant and O goes to O plus derivative of some other operator, is equivalent to say that HAB can be deformed by adding something like KA epsilon B plus epsilon A KB. And the third condition that O is a primary, namely satisfies this OPE with the energy momentum tensor, requires the Lorentz gauge condition. Now, this AP can be symmetric or antisymmetric. But if you have antisymmetric condition, then this would correspond to the corresponding gauge symmetry and gauge condition for the antisymmetric B field. But for symmetric one, this is exactly for the linear perturbation of the graviton. So the conformal invariance to the linear order indeed reproduces a graviton propagation equation. And then more generally, if you study more nonlinear situations, then at one loop level, it reproduces the Einstein equation. Okay? So these are consistent because what I did over there is a linearized version of this equation. Okay? This seems like very nice and wonderful, except that if you want to do this more carefully and study this in higher and higher loop order, it becomes very, very complicated, and we cannot control the calculation. In general, if you start with higher loop calculation, you can increasingly have lots of other tabs that you can add. For example, you can have RA, CDE, RB, CDE or many other terms that you can, and then you have R to the 3, R to the 4, etc. These are all suppressed by string scale parameters. So in the Rondinelli limit, indeed, you just get the Einstein equation. But in the higher order, this becomes out of control. But we shouldn't take bosonic string seriously anyway, because this has tachyons. So you should, what you should consider is whether we can control the calculation in the superstring setup. And fortunately, in superstring, the situation is actually much nicer. Because in bosonic string, in general, these terms are totally unknown and uncontrollable, and lots of nasty things can happen. But in superstring, actually, we can actually control what's going to happen in higher order in the loop amplitude, because it has much more mild ultraviolet divergence, and also the possible counter terms are limited by supersymmetry. So we can consider 2D. Oh, by the way, so this type of Lagrangian called sigma model. So we call this as 2D sigma model. It's a historical name. When particle physicists first introduced this idea that kinetic term may have field dependence. So here, for example, we are considering a situation where the Lagrangian has this kinetic term which depends on the field. So when it was this kind of things was first considered as a model of hadrons in 1960s, and when they started studying this, they used the symbol sigma to denote this scalar field. So the name sigma model stuck. So we call this class of model as sigma model. So if I use the NSR formalism, then the Lagrangian density is equal to 1/2 of GAB del mu XA del mu XB plus 1/2 of I of GAB psi A d slash psi B, and then there is this the other direction, psi bar A d slash psi bar B. These are left mover and right mover fermions. So this will be a natural thing. You have a kinetic term, and for both fermions and scalar field. This has lots of non-trivial interaction, because this can depend on phi or x. I mean x. I'm using x here, and so for example, this can contain Yukawa coupling of linear phi and tube size, for example. But in fact, supersymmetry requires that you also add 4 fermion interactions via Riemann curvature: A, B, C, D, psi A, psi B, psi bar C, psi bar D. Okay. So for general metric, this is a background. Okay. So this is this Lagrangian. For a general Riemannian metric, preserves n equal 1 supersymmetry. So you have 1 supersymmetry for the left mover and 1 supersymmetry for the right mover. Or maybe in general, this is not conformal, so I should write it as n equal 1 supersymmetry. Okay, but you can have more supersymmetry. So it turns out that if GAB is a scalar metric, you have, are you?
I'm just taking a picture of the classroom. Sorry to interrupt.
Okay, hello.
I'm just trying to see how many people fit in your side.
Oh, okay, so checking. So she's checking how many students are in the class. Okay, I didn't know that big brother and sisters are watching at this class. But so anyway, so if this is scalar, so that means that there is a scalar potential. Sorry, so that means that this is the target space is a complex manifold. So you can choose complex coordinate x, and the metric is scalar, which means that the metric is only has this kind of holomorphic and anti-holomorphic mixed component, and it can be written as derivative of scalar potential. As we discussed in the last couple of lectures. And the beautiful thing is that now we have, in this situation, we have full control of the beta function in the following thing. So this was studied around 1985. So you can calculate the beta function. So if you calculate the beta function at one loop, this is proportional to Ricci curvature. So this is not surprise. This was the case for general Riemann surface too. But then you calculate higher loop, you find that two loop. In fact, because of the supersymmetry, there are no two-loop counterterm, two-loop amplitude. Once you set my target space to the rich flat, you don't get two-loop divergence. You calculate three-loop, you don't get any divergence if the target space is rich flat. So you are getting confident, and physicists have this tendency that you check one, it works. You check two, it works. You check three, it works. So it works always, and that's a proof. So sometimes it's wrong. In for loop, actually people found counterterm. And it turns out that in for loop, you have a counterterm. And it contains three arcs. So this is a for loop counterterm. And give rise to divergence. And then, in general, you expect more terms. But not all is lost, because of the following. The structure is such that Rij, the beta function is exactly the following form. So it has been shown. That the beta ij is equal to Rij bar plus del I del j bar of something that is well-defined single-varied function. On the target space. Okay? So what does it mean that it's well-defined function? Well, Rij is not the del bar of well-defined function in the space-time, because this is actually equal to del I del j bar of log of determinant of G. Okay? So this is actually not a well-defined function, because determinant of G is not a scalar field. G is a metric, so it's a tensor. So this transforms like totally unsymmetric tensor because it's determinant for the holomorphic component and totally antisymmetric tensor for anti-holomorphic component. In fact, for Calabi-Yau manifold, this is omega bar. So this means that if you do the coordinate transformation, it's multiplied by some holomorphic function and anti-holomorphic function. So it changes it transforms with some holomorphic addition of holomorphic function and anti-holomorphic function. Rij bar itself is well-defined tensor because you are taking del bar, so you kill these holomorphic things. But this itself is not a holomorphic object. And the way that it is not holomorphic captures the Kähler structure of this quantity. On the other hand, this is a more trivial thing, that because this is well-defined function. So this does not modify the kind of Kähler structure. So what it means is that in general, if you do the higher loop amplitude, if you calculate the higher loop amplitude, then the metric itself has to be renormalized order by order. So you don't know exactly what is the metric in target space, which gives you exactly the conformal invariance sigma model right on the nose. But we do know that to each order in perturbative expansion, we can adjust the appropriate counter term to make it conformal. And what is great is that complex structure and Kähler class are not renormalized. So these are not renormalized. It's only the more detailed structure of the matrix that is renormalized. So Yau's theorem says that if you have a rich flat, if you have a complex manifold with vanishing first chunk class, and if you have everywhere non-vanishing holomorphic 3 form, then the complex structure and Kähler class uniquely determines the rich flat Kähler manifold, the Kähler metric. And so that data is not renormalized. So that means that there are many calculations you can do for string theory which does not get influenced, which do not affected by the fact that we have to modify the metric order by order in perturbation theory. Okay, so this is as good as you can we can do for this kind of thing. So essentially what this means is that the moduli space of conformality n equal to supersymmetric conformality theory of this type is specified by complex structure in the Kähler class. So in the last lecture, we studied the moduli space of complex structure from the perspective of classical geometry. But that space, with appropriate quantum correction by string theory, can also be considered as a space of conformal field theory also. Okay, so that's all I would like to